Okay, so let's continue. So yeah, I don't remember where we start. I'm just going to erase because we can forget that. Now, I mean, the only thing you need to remember now is that this corollary. This is where we start. This corollary, that all principal, pole, and zero divisors are divisors, finally. Good, so this is definition 4 in the notes. Now that we know that principal divisors are divisors, let's look at them more closely. So the set of all principal divisors is in a way of like embedding f in the divisor group, right? Because we take an element from f, well, non-zero, but and look at its principal divisor. Every function gives you a divisor. So it's a way of putting the functions, which I think of as a big object, but it's fairly small, only functions in the divisor group, which is huge. Like infinite, for infinite, there are infinite principal prime divisors, and for each of them you can choose a function. It's much larger. You can choose a number. You can choose a number. It potentially can be larger than the number of functions. I don't know, actually. I was thinking of something else. So the set of all principal divisors is called the group. So it's a group of principal divisors. Weird way of stating a theorem. Right? Okay. Of f over k, that's kind of the name. And we denote it by this cool p, but I'm not doing any cool scripts, so. But these are all x's, but of course x is not 0 because 0 has infinities everywhere, so when you look at valuations. And it is a group, right? So why it is a group, right? So if you take, like, it's an abelian group, so I write it with additive notation. In number theory, do it with multiplicative, but you remember it's abelian. So right, so who is the function whose principal divisor is the sum of these two principal divisors? I hope, yeah. I let it glitch. So right, so it takes times y, right? Because in divisors it's like that. Because VP of x times y for every p is VP of x plus VP of y. So it makes sense? Who is the function that gives you the identity element? Like, I need an x such that the principal. I need an x, an element, such that its divisor is going to be like cool constant, right? So I'm going to take 1. You can take 0, by the way. It's not there. You can take 1. Let's take 1. Right, exactly. So 1 and 2 and like all the elements of k are the same divisor. It's the 0 divisor. So the 0 divisor, we proved it, right? The 0 divisor, when functions, exactly those functions that don't have zeros in poles are those in k star. So you can take 1, for example. And who is the, like, what should I add to this to get 0? Like, who is the inverse? Who is the function that gives you the inverse? Right, x to the minus 1, and not minus x. X to the minus 1 because they cancel out. Right, VP here is the minus there. Good. So that's a group. And actually, it's a group, but it's a subgroup of D, right? All divisors is also a group. Oh, that went out nicely. All divisors is also a group, and it's a subgroup of all pseudo divisors, which we forget from here. So we're only working like within the divisor group, and that's a very special subgroup of it. Actually, what you really care about is the quotient. So this is the next definition. I mean, you have big groups and you care about how big is the one with respect to the other. So the group We'll talk more about it later, but let me just, the group which we denote by C, which is the quotient, right? Everything is abelian, you can take quotients, is called the divisor class group. Okay? Just a name for us. But if you know a bit of number theory, you maybe it sounds familiar to you. Okay. Maybe I should say things that for some reason I say later, I don't know why. So remark, oh, now I remember why. Okay. So if you take some element x, some function, then the dimension, and you take any divisor, then what can you say about the dimension of A and the dimension of A plus X? Right, this is the dimension of the Riemann-Roch space, right? Equality? Yeah, for equality. I'm just putting as a side here that X times LA for equality, right? Remember this thing, the shift thingy? So multiplying a Riemann-Roch space by an element, I wrote X inverse so it will work out, is the Riemann-Roch space of A plus the principal divisor corresponding to X. So it's not the same functions, these are not the same functions, but the same dimension. Okay, so this means that really the dimension of a divisor, right, so this is a divisor, and this is an element in C. Right, this is a, right, what's written here? A divisor plus P. And so what we showed here is that any element from P, right, for every X, the dimension doesn't change. The dimension is actually a property of the class of divisors here, not of each of them individually. Right? It doesn't change if you add any principal divisor. Because of that. Because this is an invertible linear transformation, so this means that these two have the same dimension. And that we proved last time. Yeah. A. Because the dimension of A is just a notation for dimension of the Riemann-Roch space. This time it's right. This is a linear transformation applied to that, and it's invertible, so same dimension. Different vector spaces, same dimension. Right. So what I'm saying is the dimension is actually all the if you take a divisor and add any principal divisor to it, namely take another representative from the same class, you get the same dimension. So it's a property of the class the divisor belongs to, not of the divisor itself. And also for degree, that's harder, but we know that now. Do you see why is this true also? Like, exactly. No, yeah, we don't know yet. So good. So yeah, that's why I'm doing it later. This is really smart. It's written. So yeah, I'm not patient enough. So, but let me just say it still, and then we will show it. So the degree of the sum of divisors is the sum of the degrees. Degrees is fine. Dimension is weird. Degrees are easy. And so this is the degree that we want. And we will show that the degree of any principal divisor is 0. Because we will show that the degree of the pole and 0 divisor of any principal divisor is the same. And so they cancel out to give you 0. Namely, every function have the same number of zeros and poles. But anyhow, so that's, trust me, but that's still true. And just with regards to this group, what I'm saying is that the two parameters we care about are actually unaffected by adding a principal divisor, and that's a very useful tool. We always do that from here on. So you move it a little bit. We kind of did it before in the weak approximation theorem, but we do those things. So just keep in mind that even if you didn't prove it yet, we prove it now. This is true. I'm not going to use it while proving it.